Okay, so let's talk about the state of a system and how do we represent that state. Remember that we have four variables, right? We have the pressure, the volume, the number of particles, and the temperature. These we are going to keep fixed in general for most of our problems, so we are only going to change P, V, and T. And remember that we have the equation for the ideal gas, nRT, or that is equal to nkVT. Okay, so let's create an ideal gas here. So now we have an ideal gas. How do we represent this guy? We're going to use what we call the PV diagram. PV diagram. Okay, and what is that? Well, we're going to have P in the y-axis, V in the x-axis, and then we measure the volume here. And let's say that is a volume V0, and then we measure the pressure right here, and then let's say that is a pressure P0, and this point here represents the state of this ideal gas, which has temperature T is equal to T0. So now we can change this, right? We can take and change the volume, for instance. Let's change the volume. So now we have a new volume, right? The volume is volume T1, right? And the pressure has increased, right? So now we have a pressure P1, which is somewhere here. And also we have a new temperature T1. So this is a new state here. We can keep doing that. We can change the volume a little more. So now we are going to have, this is V1, sorry here. Now we have a volume V2. We have another pressure here. This is my point, and this is T2. So I've changed the state of the system, and these changes here we call processes. We call thermodynamic processes or ideal gas processes. So let's go on the slide here. So an ideal gas process is what you get when you change one of the thermodynamic variables. When you change P, V, or N, right? Say you have P, V, or N, or T that you can change. Remember, N is fixed. So for instance, here we can go from this initial state where we have this volume and this pressure and this temperature to this state and then come back here, and these are processes. And this is our PV diagram. So knowing P and V allows you to find T, because remember PV is equal to nRT, and n is fixed, and we're going to assume that we know n in most cases. So this is the PV diagram, and one feature of these processes is that there are many ways to go from one point to the other. Suppose that I want to go from 1 to 3. Well, I can go by doing this here, okay, by lowering the pressure at constant volume without changing the volume, and then by increasing the volume without changing the pressure, and I get to 3. Or I can go through this process here. I can go to 2 and then back to 3. So these are two different trajectories for the same process, and there are many more. I can go through this process, I can go through doing this. There is an infinite number of ways in which I can go from 1 to 2 to 3. So an important process that we are going to need is the quasi-static process. And this is a very slow process, and I'm going to show you what I mean by that. A very slow process. So here, if I want to change the volume, I can do it really fast, like that, or I can do it very slow. Just move a little bit, then a little bit, then a little bit, then very slow. If I do it really slow, then that is a quasi-static process. If I do it really fast, if I do it fast, then that is a irreversible process. So those are the two processes that we are going to need. So when you slowly change the piston, when you move it very slow, then you get a quasi-static process. And when you do it really fast, a sudden process or imagine that you move the piston really fast after the piston broke, then that is an irreversible process. So for most problems that we are going to study in this book, we are going to assume that the processes are quasi-static. So let's look at some particular processes. One process that we want to study is the constant volume process. And the constant volume process, let's look at the simulation again. A constant volume process is a process in which you change the pressure or the temperature, but the volume of the container remains constant. For instance, here, I'm changing the temperature, the pressure changes, but the volume remains constant. If you write this equation here, if you write this, then you have PV is equal to nRT. This is constant, right? So I'm changing I could change the temperature of the pressure and keep the volume constant. In a PV diagram, if this is V and this is P, a constant volume process is this type of process here. Okay, so let's go back to the slides now. So a constant volume process is called isochoric process, and the volume doesn't change, and you can obtain this type of process by either cooling the gas or heating the gas, and this is the representation in a PV diagram. There is another process in which we maintain the pressure constant. For instance, if we have a mass here, right, the pressure in the gas is always going to be constant because this mass is not changing. And you can see that by doing a free body diagram. You have that the pressure of the gas, right, times the area of the piston have to be equal to the pressure of the atmosphere up here and the mass. These two won't change, right? So therefore the pressure of the gas is going to be constant all the time. So, and now you can heat or you can cool down, and then you can change this piston is going to move up and down depending on whether you're heating or cooling down. And this is called an isobaric process, a process in which you are changing the system, but you are keeping the pressure constant. In a PV diagram, the representation of these processes is a horizontal line like that. So let's look at a question here. We have a cylinder of gas and there is a frictionless piston here, but it's sealed tightly so the gas cannot escape. So and then you have a small flame that is heating the cylinder, causing the piston to slowly move upwards. So the piston is moving upwards as you heat. For the gas inside the cylinder, what kind of process is this? Take a minute. Well, this is a constant pressure or an isobaric process, simply because this mass is not changing, remember, so the weight on the gas is constant, so therefore the pressure that the gas is exerting uh, on this piston is constant too. So now you have a cylinder of gas that has a frictionless but tight sealed piston of mass m. The gas temperature is increased from 27 degrees to 127 degrees Celsius. What is the final to initial volume ratio? Okay, so it's 1.5, 1.33, 1.25, 10 of not enough information. Take a minute. Well, we are going to use the ideal gas equation. You have let's go back here. Going to use the ideal gas equation, right? So we have PV is equal to nRT. So then we are going to say P initial, V initial is equal, N is not going to change, R doesn't change, T initial, and then you're going to have P final. B final is equal to nR T final. So you know the initial temperature, which is 27 degrees. You know the final temperature, which is 127 degrees. And you you know that the pressure is constant, right? So these and these are the same, right? Because the mass here, this guy moves, but the mass doesn't change. So P final is equal to P initial. So then I can divide V final by V initial. These two cancel, and then you get T final divided by T initial. And then here it would have been I and I. And then that gives you your answer, which is 4 divided by 3. All right, thank you.